Hey, hopefully this cute little guy will make it easier to take notes today. So I just wanted to go over this next theorem called the factor theorem. And it says a polynomial f of x has a factor of x minus k if and only if f of k equals 0. And so this is directly tied to this remainder theorem that we had the other day, where it said if a polynomial f of x is divided by x minus k, then the remainder is f of k. So right here, if f of k equals 0, that means the remainder is 0. So if the remainder is 0, then that means that this x minus k divided into it evenly. So it was a factor. Where I don't think the remainder theorem is terribly important because we can find the remainder just by going through synthetic division. I did go through it with you because who knows, it could be a question on an SAT test. Use the factor theorem or use the remainder theorem. And if so, then you've seen it and maybe you'll know what to do. But the factor theorem is important. It means if we go through synthetic division and we get a remainder of 0, that x minus k was a factor and k was a 0. So that's important. Let's do an example. I'm just working in the book if you want to work along with me. This is number 18. I'm sorry, page 118, example 6. Show that x minus 2 and x plus 3 are factors of f of x equals 2x to the 4th plus 7x to the 3rd minus 4x squared minus 27x minus 18. So we could do long division or we can do synthetic division, but I think it's much easier since this fits that x minus k form to do synthetic. So k is 2 for the first factor, or we're trying to show if it's a factor. So we'll do synthetic division with it. Our degrees are 4, 3, 2, 1, and none. So they're in perfect order. We're ready to just write down the coefficients. 2, 7, negative 4, negative 27, and negative 18. We always bring the first one straight down. Then we start multiplying. 2 times 2 is 4. We add 7 and 4. 2 times 11 is 22, and we add. 2 times negative 18 is negative 36, and we add. 2 times negative 63 is a negative. I don't think I did something right. 2, 7, negative 4, negative 27, and negative 18. 2 times 2 is 4, and I add. 2 times 11 is that. 18. Huh. Oh, I knew I was wrong somewhere because this was supposed to work out to have a remainder of 0, and my numbers were getting larger and larger. 2 times 11 is 22, and I add and get positive 18. 2 times 18 is 36, and I add and I get a positive 9. 2 times 9 is 18, and I add and get a 0. That's our remainder. This is our constant. This is our x squared, and our x to the 3rd. So put addition symbols in there since they're all positive. So we did show that x minus 2 is a factor because it went evenly. Now, you have options. You can completely repeat the process with this factor, knowing that it was x minus k, so k would be a negative 3. Or we can start here with where we were. So we can start with the 3. Let me back up a little bit. Delete a bunch of stuff. So I can also just start right here with the k being -3, and I can divide again with the -3 out here. That's what the book means in the directions here, where they have repeated division as the title for this example. Bring the 2 straight down. -3 times 2 is -6. Add. -3 times 5 is -15. Add. -3 times 3 is -9. And add. We don't do anything with this. So we got a remainder of 0. That's our constant. That's our x, and that's our x squared. Since our remainder was 0 again, the -3 is also a 0. So x plus 3 is also a factor. And that's all they asked us to do, show that they were factors. But we end up with this polynomial, 2x squared plus 5x plus 3. We could keep going. We could keep factoring and find all the factors. I think if you check your outer and your inner, you get 2x and 3x, which is 5x. So these are all of our factors. So really, f of x is the same thing as the x minus 2 that they gave us, x plus 3 that they gave us, and these last two that we found. That's the complete factorization of it. That's 1, 2, 3, 4 x's that would get multiplied together for an x to the 4th. And that's how f of x started. So if you multiplied all these together, you would get this function right here. Okay, example 7. Okay, before we do example 7, we need to talk about this thing called the rational zero test. All right, I'm going to pause and write it down. It's on page 119 if you also want to write it down. Okay, so here is your rational zero test. Pause it so you can get it written down. This is our next big topic. If f of x is a polynomial with integer coefficients, so our coefficients for the whole polynomial have to be integers, like positive and negative whole numbers. No fractions, no decimals, nothing weird. Then every rational zero of s has this form. The rational zero would be p over q, where p and q have no common factors other than 1. P is a factor of the constant term, and q is a factor of the leading coefficient. So P is constant, and Q is leading coefficient. Let's see how we work this out. So example 7. Find the rational zeros. Of f of x equals x to the 3rd plus x plus 1. Let me go back for a second. This is only going to help us to find the rational zeros. Any zero that will be able to be written as a fraction, like a ratio. So it'll help us to find zeros of whole numbers. So it's going to help us to find the rational zeros, the zeros that are positive or negative numbers, or their fractions, or their repeating decimals. It won't help us to find the irrational zeros. So if for some reason our polynomial function has a zero that's like at pi, or a number's like pi, like 3.287 and so on, and it never repeats and it never terminates, it won't help us to find those. But we can find all the rational zeros. So we're going to find the rational zeros of this. To find the zeros, we always try to factor. Well, we just have been talking about factoring. This has no GCFs that we can factor out, and it's got 3 terms. The way we factor with 3 terms is we do the magic method and we try to factor it into 2 binomials. This is not a quadratic, so I can't do that with this. So I'm stuck. I have no way to go on until I remember I know the rational zero test. So we can find our, I always say, possible rational zeros are equal to P over Q, where P is the constant and Q is the leading coefficient. So P is our constant and Q is our leading coefficient. So, wow, we're dealing with 1 as our constant and 1. So these can be positive or negative. So it could be plus or minus 1 for P or plus or minus Q. 1 for Q, which 1 divided by 1, either way you go about it, you're going to get plus or minus 1. Those are the only possible rational zeros for this. It's either 1 or positive, negative 1 if it exists. So we can do synthetic division with this to see if they're zeros. So let's try positive 1. So we set it up and we check our polynomial. It goes 3, it skips x squared, and then it does 1 and none. So we're going to have to do a leading coefficient for x cubed, a 0 for x squared, the 1 for the x, and the 1 for the constant. Bring the 1 straight down. 1 times 1 is 1, add. 1 times 1 is 1, add. 1 times 2 is 2, add. There wasn't a 0 remainder. So x equals 1 is not a 0, since we didn't get our remainder of 0. So now we're going to do the same process with our negative 1, using those same coefficients. Bring your 1 straight down. Negative 1 times 1 is negative 1, add. Negative 1 times negative 1 is 1, add. Negative 1 times 2 is negative 2, add. Shoot, something didn't work out right. I doubted myself there for a second. That didn't work either. So x equals negative 1 is also not a 0. And if you were to graph this on your calculator, then that's your last option to find your 0. You would try to graph it on the calculator, and you would do the, put it into y equals, and you would do the second calc 0. And this is the graph you would get. And then you want to find the value of this 0 right here. So if you do second calc 0, just like we do second calc for min or max, then it's going to say at the bottom, it's going to say left. So you're going to arrow a little to the left. Then it'll say right. So you'll enter, and then you'll arrow a little to the right and hit enter. And then you'll try to get right where you think that 0 is and hit enter. And it will give you the solution. And when you see what it is, it'll be x equal to some number that's not a rational number. And that's all we can do. All right, let's do another. Let's do one that might work out. Example 8. Find the rational zeros. And I start abbreviating this. Find the rat zeros of f of x equals 2x cubed plus 3x squared minus 8x plus 3. So I use the rational zero test as a last resort. Sorry, I keep flipping this around. I'm always going to try to factor it first. If it factors, then great. That's much easier. But this one does not have a GCF. I try to factor by grouping. And when I factor out my GCF, and this has a GCF of a 1, my parentheses don't match, so it does not factor. And I can't group it by 3 and 1 like we did today either and get anywhere. So I can't factor it, so I'll have to use the possible rational zero test. So possible rational zeros are P over Q. P is the constant, Q is the leading coefficient, and it can be positive or negative of those numbers. And then you list out all the factors of 3. How can you get 3? 1 goes into 3, and 3 goes into 3. And all the factors of 2 are 1 and 2. See, we didn't have to do that over here because the only factors of 1 were 1 and negative 1. So all the possible rational zeros are all the possibilities here. So watch what we can do. We can get 1 over 1. So plus or minus 1 is an option. And also, I'm going to have to leave that. And also I could do the positive 1 over this 2. So plus or minus a half is also an option. And then I think I will delete these and just so the circles make more sense. So that gives me plus or minus 1. Oh, I'm going to have to delete all that. The next one is taking the 1 and putting it over the 2. We just want all the possibilities here. So that would give us plus or minus a half. I'm going to go ahead and delete that so I can draw my next 0. We've used the 1 with the 1 and the 1 with the 2. So now we can do 3 over 1. So plus or minus 3 is an option. And then we can also do 3 over 2. So plus or minus 1, plus or minus a half, plus or minus 3, and plus or minus 3 halves. Ms. Stewart, we have 8 possibilities. Yes, you've got 8 possibilities, but think about all the numbers there are between negative infinity and positive infinity, and you've narrowed it down to 8. So that's good. And then what we do is we say, well, which one do I think is going to work? And we just try one. We think, oh, I'm thinking that 3 might work. So let me do synthetic division with 3. So I check my polynomial, and it's 3, 2, 1, none. Perfect. Write down those coefficients. Bring the 2 straight down. 3 times 2 is 6. Add 3 times 9, 27. Was that 19? 3 times 19, 57. That definitely does not give me a 0 remainder. So that one didn't work. And then you just try another. I might go ahead and try, I'm going to go ahead and try 1. I love 1. Bring the 2 straight down. 1 times 2 is 2. 3 plus 2 is 5. 1 times 5 is 5. Negative 8 plus 5 is negative 3. 1 times negative 3 is negative 3. Yay! So 1 worked. That simplifies it. It might simplify it to, I think it does. This is the remainder, constant x and x squared. It might simplify it to a quadratic that we can factor. Let's see. We got the 2x and the x and the 3 and the 1 and the plus and the minus. Check your outer and your inner. So that works. So this first factor gives us another rational 0 of a half, which we had. And this one gives us a rational 0 of a negative 3, which, I should have just tried the negative. So the positive one worked. So the rational zeros were 1, a half, and negative 3. Those are my solutions. Those are my intercepts. Those are my roots. Okay, we're going to do one last one, and I'm going to help to narrow you down a little bit. Find the rational zeros of 6x to the third minus 4x squared plus 3x minus 2. This one might factor by grouping. No GCF. Factor by grouping. We could take a 2x squared out. 3x minus 2. Ooh, that's exactly what I have there. So let's take a 1 out. So our parentheses match. So we'll factor out that 3x minus 2, and we'll write down what's left. And those are our factors. So let's let the rational zero test back us up and help us. Or just to show that we can get the same thing that way in case this one hadn't factored. So let's pretend like it didn't. So the rational zero test says it's P over Q. P is our constant. Q is our leading coefficient. So we're dealing with plus or minus 2 over plus or minus 6. Factors of 2 are 1 and 2. Factors of 6 are 1, 2, 3, and 6. So of all the numbers in the world, these are the possible rational zeros. All the combinations that we get. 1 over 1, 1 over 2, 1 over 3, 1 over 6. 1 over 1, 1 over 2, 1 over 3, 1 over 6. And also do the same thing with the 2. 2 over 1, which is 2. 2 over 2, which is 1. We already have it. 2 over 3. And 2 over 6. And 2 over 6 is a third, which we already have it. So, of all the possibilities in the world, we've narrowed it down to these. Now, that's a lot of choices. 1, 2, 3, 4, 5, 6, 12 choices. And I could be so unlucky as to try all the ones that don't work before I try the one that does. So, why don't you use your calculator? I want you to go ahead and graph it and look at where it looks like it crosses the x-axis. So as you're testing it, my room just turned dark. So if you graphed it, it looked like somewhere between 0 and 1, it crosses the axis. And you can do the second calc, the 0, and get that value. And if you go through that test, you'll find that it's the 2/3. It might come up as 0.666 repeat. So, but the 2/3 is the one that works. So let's go ahead and, now that we've used our calculator to help us, we're going to try 2/3. So set up your synthetic division. 6, -4, 3, -2. Bring your 6 straight down. 2/3 times 6 is 12/3, which is 4. -4 and 4 is 0. 2/3 times 0 is 0. 3 plus 0 is 3. 2/3 times 3 is 6/3, which is 2. -2 times 2 is 0. Yay! So 2/3 works. It backs us to a function that is remainder, constant, x, and x squared. So our function becomes x squared equals 0. Whoops. No, it doesn't. Our function becomes 6x squared plus 3 equals 0. And now we can solve this for x. Minus the 3 on both sides. Divide both sides by the 6. Simplify. Take your square root. Oh, I didn't simplify. Whoops. Take your square root. So x is plus or minus I square root of a half. Technically, I should change that to I times square root of 1 over square root of 2. And I should rationalize with that square root of 2. So that would become plus or minus I square root of 2 over 2. Regardless, though, if we're doing real zeros, the only real zero we would have would be the 2/3. These are the complex zeros, the imaginary zeros. All right. So if you feel like you've got a good handle on it, you could stop the video now. If you feel like you could handle another example, I'm going to go through example 11, which is the same process. Totally up to you. Finding the real zeros. I don't believe this factors nicely. Let's see, we can take an x out. But I don't think we would be able to factor it by grouping. But bringing that x out, that gives us a 0. X equal to 0. We've got one of our zeros already. Just 3 more to go. Okay, so let's use this and let's do the possible rational zeros. So the rational zero test says of all the numbers in the world, we can use P over Q, constant coefficient. So we can do plus or minus 1 and 2, all the factors of 12. And on the bottom, all the factors of 10. So I've seen on SAT tests before something where they asked for the list of all the possible rational zeros. And you would give them what I'm getting ready to do here. You would take the numerator for each one of these numerators, you would put it over the denominators, and you'd write down the number or the fractions that you would get. And you do that for each numerator. So you get 1 over 1, 1 over 2, 1 over 5, and 1 over 10. It's messy. And then we're done with 1. So now let's go with the 2. You get 2 over 1, 2 over 2, which is 1, 2 over 5, and 2 over 10, which is 1/5, and we already have it. Done with 2. Now let's go with 3. 3 over 1, 3 over 2, 3 over 5, 3 over 10. Done with 3. Let's do 4. 4 over 1, 4 over 2, which is 2, 4 over 3, I'm sorry, not 3. Goodness. 4 over 5, and 4 over 10, which is 2/5, and we already have it. 6, we'd have 6 over 1, 6 over 2, which is 3, 6 over 5, 6 over 10, which is 3/5. And lastly, we'd have 12 over 1, 12 over 2, which is 6, 12 over 5, and 12 over 10, which is 6/5. Now that is a lot of possibilities, but it's still a lot less than negative infinity to positive infinity. I would definitely plug this into the calculator and look to see what a 0 might be. And if you do that, I think you might find that 2 works. Might be lots that work. But let's go through synthetic division with 2, because it was one of our possibilities. I'm going to write down the coefficients, the 10, negative 15, negative 16, and the 12. Bring the 10 down. 2 times 10 is 20. Gives you a positive 5. 2 times 5 is 10. Gives you a negative 6. Gives you a negative 12. Yay! Then possibly, if that's the constant, remember we already divided one x out, and we just divided another one. So that's not the constant. This is our remainder. This is our constant. That's our x. This is our x squared. So we have 10x squared plus 5x minus 6. I know I can solve this. Whether it factors or not, I can at least do quadratic formula. Magic method, first times last, middle. If that's a minus, we've got plus and minus, and we subtract to get 5. Factors of 60. I don't think it's gonna 7, 8, 9, 10. I think that's all of them. There is no way to get 5, so we're gonna have to do the quadratic formula. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. X equals negative 5 plus or minus square root 25. Let's see, negative 4 times 10 times negative 6 is a positive 240 over 220. That's a positive 265 over 20. We have to break that thing down. 5 and 5 and 3. Yep. 53 is prime, I believe. I don't believe that simplifies at all. Those are my other two answers right there. So my zeros are the 0 we got at the very beginning when we factored the x out, the 2 that we found with synthetic above, and then negative 5 plus square root of 265 over 20, and negative 5 minus square root of 265 over 20. And these numbers that we just found here, they're not rational numbers, because anytime you have a square root of a number that's not a perfect square, it's going to be irrational. So 265, we tried to factor it, it did not factor, so it's not a perfect square or even factorable. So it's irrational, just like pi. So 0 and 2 are only two rational zeros. Alrighty, good luck.